So there, if you look at carefully about those equations, then you can find a relation between clock-based performance and power-based performance. So power-based performance can be represented by clock-based performance divided by alpha max coefficients. So based on these equations, then we can simply observe that it is important to design the logic to obtain maximum clock-based performance to save power. This slide describes the methodology, how to estimate the performance in GPUs and FPGAs for mixed precision solvers. We simply employ Megama version 2, Megama version 0.2, because it's highly tuned GPU code. And we tested Megama 0.2 with Tesla intensity and IntelliJ 2.97 GHz multiple. For the evaluation for the FPGA, then we employed performance modeling in Xilinx participated FPGAs, which is XC5-330 with the previous work. So in the previous work, then the previous is ported to Cray XC1 in 2008, and in the previous work, one processing element has one multiplier and one adder. So two floating point operations can be done in one clock cycle. So based on this fact, then we can predict the FPGA performance following by these equations: 2 flops times number of processing elements times clock rate. We employ 0.12 GHz for the clock rate based on Xilinx press and our report. So when you look at the table, if the condition number is small, then we can employ 192 processing elements, which is large number of processing elements. If the condition number is large, then we can just employ few number of processing elements. So when the condition number is small, then we don't have to employ the precisions having this kind of range, because it's just loss of performance. I'll talk about the result we obtained. So this plot represents the performance using Tesla system. So the first line, here, it represents by power-based performance. The second one is represented by clock-based performance.
Where are you pointing at?
Oh, what's that?
Can you show me where you're pointing at?
Oh yes, the power-based performance is represented by this first column.
I don't see a red dot on there.
Oh, can I see that?
You'll have to walk up to the screen.
Well, just point it. Am I blind?
Finger. There it is.
Just use your hands on the. Just move up to it. Point to it.
Oh, okay. So the first column is represented by power-based performance. Thanks.
Back to the future.
That's why I carry it with me.
And this one is clock-based performance. And this one is just performance we know about the graph. So in the GPU, there is distinguished line here, because you just employ single and double precisions. So when you employ single precisions, then you can achieve around 200 gigaflops in mixed precision solvers. When the condition number is large, then you have to employ double precisions. So double precision can achieve around 60 gigaflops in Tesla system state. When you observe the metric size, then metric size grows, the performance can also grow, because the parallelism we can exploit in the mixed precision solver can also increase. And these slides talk about the performance from the FPGA. When you look at the FPGA, there is no distinguished line, because FPGA can use actual precisions. So when you look at the graph, the performance can be grow quadratically according to the condition numbers. And when the metric size is getting large, then performance is getting large. Performance is getting improved as well. So FPGA can obtain around 45 gigaflops when the condition number is small. When the condition number is large, we can achieve around 5 kiloflops. So it is really hard to see, like about the power performance comparison between GPGPU and FPGAs. So we fixed the matrix size with distance size, which is 8K times 8K matrix. So when the matrix size is fixed with 8K times 8K matrix, then the time-based performance, for the time-based performance, GPGPU shows better than FPGAs, around 4 times. But when you look at the clock-based performance, then FPGA shows around 2 times better than GPGPU when the condition number is small. When the condition number is large, then FPGA shows slightly better than GPGPU in clock-based performance. And this is about power-based performance. So power-based performance shows similar with clock-based performance because it is directly related with clock-based performance and power-based performance. So when the condition number is small, the FPGA shows around 2 times better than GPGPUs. When condition number is large, then GPGPU and FPGA performance looks similar. So in the conclusions, then FPGAs can employ arbitrary precisions, while GPGPUs can employ either single or double precisions to exploit the precisions. So in order to save power,